Okay. The bias problem is actually quite old on. Already in the first conference on cosmic wave 77 IAU symposium, it was clear that there are differences between the distribution of galaxies and n-body simulation. Here there are large regions completely void of galaxies, and here we see in low density regions particles. And this difference was called biasing. No, Nick 1984 gave this name. And here it's according to better, newer simulation. Left we see the whole dark matter stuff. And here we see only high density regions of the same field where low density particles are not taken into account or are excluded. And the biasing is the problem is how to relate these two density fields. It was clear already quite early, Ostreicher and Sen in 92 showed that here is a total density and galaxy density. In low density regions, galaxies cannot form. And roughly they estimated bias value 1 point using correlations. And recent data by Springel using simulations, here is dependence of bias on time, different epoch, and we see that on present epoch it is very close to 1. That means galaxies follow matter. And the question is why such large discrepancy? Here is one more problem. Together with NSAR, we studied the evolution of the fraction of matter in voids. And we found that roughly they are related, bias parameter is related to the fraction of matter in voids. And by definition, fraction of matter in here is in clustered population, here is the voids, and here is his analytical estimate. Here is formation epoch. If it's just now then the fraction is roughly in this range, and it decreases with time. And it is possible to calculate using numerical simulations how much matter is in high density regions and in low density regions, and this is independent check of the biasing. Now in the present study we use these new simulations. We applied correlation analysis. We find bias function, and using two different kinds of test objects. One is simulated galaxies, and the second is just dark matter particles. In simulated galaxies, we have their magnitudes. In particles, we have local densities. And the goal is to find the relation between various parameters, both for galaxies and for these clustered dark matter particles. But taken into account this the fraction of matter in the clustered population. Here is a picture. Here is top is all dark matter at 3 different redshifts, and here is a high density part which corresponds to galaxies. Here most of the volume is void, and the fraction of clustered population, it increases with time. Just matter flows from voids to clusters. Here is roughly the distribution of magnitudes. This is in brand, and here is a local density, densities of particles, which take into account both dark matter and stellar matter, so total density. And in both cases, the range of densities is very large, but the distributions are different. That means that they represent slightly different properties of the web. Here are correlation functions. Now they look quite similar to earlier results. The top is using galaxies, and here is using dark matter particles. The solid lines here is whole total dark matter here, and here are clustered populations, galaxies. And when we divide this function to this function, we get this is the bias function. Bias function is interesting, and there are several important properties. On small scales, the bias function characterizes the properties of halos. And to determine the bias parameter, we use separation 10 megaparsecs. It is here. Here is influence of halos is already weaker, and this defines the bias parameter itself. And here, when we compare these two variants, one is using galaxies and using dark matter particles. Here is in close to 1, the bias function is very low, or even slightly less than 1. This is one of the basic properties of galaxy bias functions. Here it is not so. You see it is flat here. And second interesting property, when you look here for different magnitudes, they almost coincide here. Here is the magnitude limit. Here is very bright, galaxy is very faint, and they almost coincide. Now, when we take this look in more detail, here is the bias parameter, which is found in separations 10 as a function of magnitude, and here log density, and here is different redshifts, and we see that it is very flat here. That means that all faint galaxies have the same bias parameter as bright ones. And the only possibility to explain this is that they occupy the same regions, in the same halos. There is no population of very fine galaxies in the field, otherwise it would be difficult. With dark matter particles, there are dark matter particles in the field, the trend is different. Here is also interesting. When we take very low density here, roughly here, then all dark matter particles, this sample has all dark matter particles, and by definition B is here 1, but here is not. Now, when we take as characteristic parameter the bias value for the lowest luminosity galaxies, this B1, and compare how it evolves. Here is a redshift, here is for galaxies, and here for dark matter particles. We see that both simulations, 100 and 300, they have roughly similar dependence, but the value here is very close to 1. Here is different. It is larger, and here we calculated the blue line here. Blue line is calculated from the fraction of matter in the clustered population. This the density distribution is known, and it is easy to find this independently on the correlation analysis, and we see that this variant of correlation function using dark matter particles, this is in accordance with this dependence, this theoretical expectation. This means that bias parameters of galaxies and dark matter, they describe different properties of the cosmic wave. Why it's so, it is not so clear. When we are already almost end here. The first result is that bias parameters decrease during evolution. This is a well-known result. Just the physical reason is clear. Matter flows from voids to high-density regions. Second important parameter is bias parameters of low luminosity galaxies are equal. That means that the absence of dwarf galaxies in voids. All dwarf galaxies are in the same halos as dark ones. There are some fainter such clusters in voids too, but they are not completely, they are part of the clustered population already. This bias parameter, which is found from using dark matter, is in accordance with this theoretical explanation. Galaxy density field contains very many cells of zero density, and it has influence. That means that always there is some dark matter in voids, and by definition, in this case, B must be 1, larger than 1. So the final conclusion is the two types of correlation functions, galaxies and dark matter, they define different properties of the cosmic wave. For other properties, we have found explanation, but here it is still open. We don't know why this correlation function for galaxies, why it is in conflict with this dependence. And this is the basic result of our study.
I don't understand your point 2. There exists no population of field dwarf galaxies.
Yeah.
But I know hundreds of them. I know hundreds of field dwarf galaxies. What does that mean?
Look here. Bias parameter is for low luminosity galaxies constant. This is here. It is constant. It depends on time, of course, but for every epoch it's constant. That means these particles are located in the same halos.
But that's in the simulations, not in the real universe.
But I don't understand your statement that there are no dwarf galaxies in the field.
Yeah, they are in filaments, and this is it's a clustered population. That actually filaments are very different richness, but very fine filaments are only dark matter filaments. But if they are stronger, they contain stellar matter too, and this stellar matter is in the same clumps for different galaxies of different magnitude. This is the point.
It must be a semantic thing here. We can talk about it after, because I just don't quite grasp why you say there are no dwarf galaxies in the field.
The point is, in these simulations, apart from being adaptive spatially in order to get high res, you actually need to be adaptive in K space, how you set up the initial conditions. And you need to go to higher K in voids in order to see these dwarf galaxies forming. And so it's a question of how the simulation was actually set up. I think that solves your problem.
Actually, I used the catalog of galaxies as found by authors of these simulations.
But they all do the same thing.
I haven't checked the method, how they do this. This can be checked, of course. But anyway.
Do you agree with what I said, Nick? Yeah, he was nodding.
Yeah.
Oh, it's the 300, that is
yeah, both 300 and 100, they have the same properties.
Right. Thanks. I also want to kind of express my opinion on this. It seems to me the fact that the bias value of galaxies chosen from simulation is converging to 1 is saying that the clustering pattern of these galaxies are exactly the same as the whole dark matter field. And you've also stated that in the beginning, if we look at dark matter only simulations, then the voids are not empty, right? They have some probability of having some mass there. So this seems to me it's already saying that there will be some low probability that galaxies will exist in voids. Isn't that not the case?
Actually, here we consider the whole simulation box as a unit. We don't discuss different voids, different regions.
Yeah.
It's a different topic.
Yeah.
Yeah, it's a whole box.
Sure. But it seems to me that the perspective of looking at the probability of galaxies populating voids or not is seen in this the fact that their biases is close to 1, and therefore that infers that the galaxies will populate the whole box in the same way as the dark matter do.
I cannot comment now.
All right.
Yeah.
You're saying the bias is 1, so it will follow the dark matter.
Yeah.
No, actually here, the limit of galaxies is roughly here. This part corresponds to dark matter, which is rarefied. Here we go to, when we go here, we go to different regions of different density. And this is density for the faintest galaxies, and here is for the bright galaxies. And this part here, left to 8, is dark matter only, without any stellar matter. This is the difference. So these bias functions are different because different test particles. One is real galaxies, not simulated, and the other is dark matter independently if it corresponds to a stellar dark matter or just void dark matter. This is difference.
Yeah, I just wanted to comment on this, that I understand that one interpretation that there is a constant range in which there is a range of luminosities in which the bias is constant would be that the galaxies are in the same halos. But another interpretation would be that they are in the same range of halos with the same mixture, just like, for instance, dark matter is in halos, and the dark matter itself has a bias of 1 by definition, and it is, if you take all dark matter, it's kind of constant, and it's a mixture of halos based on the halo mass function. So if all these galaxies have the same bias, it doesn't necessarily mean that they are all in the same size halos, just that statistically they spread over the same range. And because their bias is actually very close to 1, I agree with Sarah that one possibility is that they start to track dark matter, as from the work you mentioned earlier is even the dynamical evolution of galaxies is that they eventually, as time goes on, will follow the dark matter distribution. So I think that means that they could be in a range of halos and not just one particular type of halos. That's another interpretation.
Are there other assessments? Okay, I think this looks like you see what's going to happen over lunch. There's going to be more discussion. So let's thank Jaan again.